Hey, good morning, everybody. This is Mr. Ainsworth. We're going to get into Section 2.1, Part 2, and finish this lesson here. And we're going to start off with a theorem. It's Theorem 2.1 in your book, and it's about differentiability and continuity here, a function being continuous. And it states this, that if f is differentiable at x equals c, if f of x, or if f, all right, is differentiable, kind of a cool word there. If f is differentiable at a certain location, we'll call that at x equals c. Could be at x equal 2, x equal 5, at any point on the x-axis there. Then the theorem states that f of x, our function that we're considering here, is continuous at that point. Is continuous at x equals c. Okay? And what that is implying is that if a function is differentiable, then it's continuous. Okay? In short, differentiability implies continuity. Okay, let's put that in red. This is what it implies basically. Differentiability, okay, implies, okay, continuity. All right, so if a function is differentiable at a specific location, call it x equals c, then it's continuous there. All right, differentiability is continuity. So if I tell you that a function is differentiable everywhere, then it's continuous everywhere. That's what I'm talking about. Okay, but the question is the converse true? Does continuity imply differentiability from right to left? All right, and that's my question here. Does continuity imply differentiability? And the answer to that question is no. All right, because there are many cases where a function's continuous everywhere, but not differentiable everywhere. Okay, because there are functions here. I should have put this in black here. There are functions which are continuous everywhere, but not differentiable everywhere, which are continuous everywhere, all right, but not differentiable everywhere, but not differentiable everywhere. And I'm going to show you a few here in the lesson. Okay, so just because it's continuous doesn't mean it's differentiable. All right. However, the theorem 2.1 states here that if it's differentiable at a specific location, call it x equals c, then it's continuous at that point, x equals c. So differentiability implies continuity, but not the other way around. So let's get into a little discussion here on the different ways a derivative fails to exist, and go through the different types and explain each one. All right, the first type, or the first case where a function may not be differentiable, is a sharp term or a cusp, or what we say at a vertex. Okay? So let's take a look at a function which has a vertex, like the absolute value function. Absolute value functions, as you saw in Algebra 2, are continuous everywhere. They're continuous everywhere. There's a little typo right there. All right, but is it differentiable at the vertex? All right, does a tangent line exist at the vertex 2, 0? That's where the vertex of this absolute value function is. In other words, is f of x differentiable at x equals 2? We're going to prove that it's not. And to do that, what we're going to do is we're going to take a look at the alternate form of the limit definition. It's located on page 101 in your text, and it outlines it there and gives a great example. I'm going to do it here. And we're gonna use this definition here, f prime of c, which is the derivative of f at c now, okay? Because we want to see if it's differentiable at a specific location. In this case, at x equals 2, is equal to the limit as x approaches c. In this case, is going to be 2 of f of x minus f of c, all divided by x minus c, provided that the limit exists, and that happens when the left and right hand limits are equal. So we're going to have to take a look at that. What's the left and right hand limits? If they're equal, the limit exists and it's differentiable at that point. If the limits are different from left and right, well, then the limit doesn't exist, and therefore the derivative doesn't exist at that point. And therefore the function is not differentiable at that point. So before we go into my specific example on this absolute value function, we've got to see why this limit definition makes sense. Okay, and this is discussed in the textbook as well, but I'm going to discuss it here first. So I'm going to draw a little graph here. I'm going to take a look at a function. Let's call this f of x. All right, there's our function here. And I want to take a look at why this makes sense right here. Why is the derivative of f at c equal to this limit? Well, let's take a look at a situation here. Let's suppose that this right here is c. And we want to find the slope of the tangent line at c, which would be approximated by this tangent line right here. There's f prime. All right, now what are the coordinates at this point? Well, it's c comma whatever f of c is. So this point right here is c comma f of c, c comma f of c. And let's consider this point up here. We'll call this point P like we usually do, and we'll call this point Q like we usually do. And let's suppose this point right here at Q is x comma, well, it's going to be f of x, right? So f of x right here. So x comma f of x in general. And what we want to do is approximate or use the secant line through PQ to find the slope of the tangent line, just like we did in an earlier lesson here. Well, we did it a little bit differently before, but what we want to do is get P or Q here infinitely close to P. To do that, I've got to slide Q along the function right here, and what's going to happen is that x is going to approach C. So I want to slide Q along the function here and get infinitely close to P. To make that happen, I have to have x approach C. All right, so what we're going to do is I'm going to find the slope of the secant line, and then I'm going to take a limit. Okay, and that's going to give me the slope of the tangent line at P, which is f prime of C. So in this case, I've got I need to take a limit as x approaches C here of the slope of the secant line. And what's the slope of the secant line? Well, it's the difference of the y values, f of x minus f of c, all divided by the difference of x values, and that's going to be x minus c, or the distance between x and c. So this is the slope of the secant line, and then I want to take the limit as x approaches c because I want to get q infinitely close to p here. So I can take the slope of the secant line and have it converge to the slope of the tangent line at p. All right, and this is equal to f prime at c, which represents the derivative of the function at c. Okay, so I just took the slope of the secant line from PQ, slope of secant here. I took the limit as x approaches C to get the slope of the tangent line directly at point P, which has coordinates c comma f of c. All right, so let's use this alternate form of our limit definition here and apply it to our absolute value function and show why it's not possible to have a derivative or a tangent line at a vertex or a sharp turn is what we call it. Okay, now again, look right here. The vertex is at 2 comma 0 here. This is 2. And to start here, what we're going to do is recall the absolute value definition. The absolute value of x is equal to x here if x is greater than or equal to 0, and is equal to the opposite of x if x is less than 0. Okay, there's your basic definition of absolute value that you saw last year in Algebra 2. So for us over here, if we consider y equals the absolute value of x minus 2, well then it must be equal to x minus 2, okay, if x minus 2 is greater than or equal to 0, which means x has to be greater than or equal to 2. That's to the right of 2. Okay, that's going to help me form the right-hand limit here as we evaluate the derivative using the limit definition. And then it's equal to the opposite of x minus 2 if x minus 2 is less than 0 or if x is less than 2. Okay? Now whenever you're going to use this alternate definition, you have to come in from the left and to the right. So what we're going to do is we're going to analyze the left-hand limit first. Okay, so let's do that. Let's take the limit here of our function coming in from the left of 2. Okay, that's called the left-hand limit. Well, if you're left of 2, that means that you're going to be less than 2, which means you're going to have to evaluate the second part. Okay, and it's the function minus f of c. So using this definition up here, we got f of x, which in this case is the opposite of x minus 2, minus, okay, the function evaluated at the point we're considering. And we want to investigate what happens as we approach 2. So we're going to have to evaluate f of 2 here, the function at 2, and divide that by x minus c. But what's c? Well, it's 2. Okay. So we simplify this a little bit, and we get the limits as we approach 2 from the left of what? Let's distribute through the negative here, and we get negative x plus 2. F of 2, what's that? We substitute it into the first part of your function here, because you've got to look at the domain. 2 is greater than or equal to 2 here, so you evaluate the first part. And that's going to be, let me just make a little note here. Using this, f of 2 is going to be equal to 2 minus 2, or obviously 0. So I'm going to put plus 0 there, or minus 0, excuse me. All divided by x minus 2. Okay, so what's that? Okay, so you know what? It'd be a whole lot easier if I didn't distribute through the negative. Let me change that right here. Okay, let me write it as the opposite of x minus 2. So don't distribute through the negative. You'll see why right here. It's because I want to simplify a little bit. That becomes 1. And so I get the limit of negative 1 as x approaches 2 from left. And as you guys know from previous chapters, that the limit of a constant is constant itself. So you get negative 1 here. The limit of negative 1 as x approaches 2 from the left is still negative 1. And if you notice that, that's the slope of the left-hand side here. If you consider the slope of the tangent line at any point on the left side of the graph, okay, since it's constantly negative 1 there, we should get negative 1 because the slope of the tangent line is negative 1. It's constant on the left-hand side. Okay, if the derivative exists, then the limit exists at x equals 2. So we have to come into the right. All right, and hopefully it's the same. If it's not the same, the limit doesn't exist, and then it's not differentiable at 2. Remember, the derivative is a limit. So if the derivative exists at specific points, then so does the limit, and vice versa. If the limit doesn't exist, well, then the derivative doesn't exist at that point. That's the whole point of this discussion here. Okay, so we want to take f of x as we come into the right. So which part are we talking about if we're coming in from the right? If we're to the right of 2, well, then you've got to be greater than or equal to 2. So we're talking about the first part of the function here, which is x minus 2, minus f of 2, okay, which we already know is going to be 0, all right, divided by x minus 2. And what's that? Well, it's going to be x minus 2, well, the limit of that. As you approach 2 from the right of x minus 2 divided by x minus 2, all right, which is going to be 1, of course, and the limit of 1 is 1 as you approach anything. And this is the right-hand limit. And notice that these are different. And because the limits are different, all right, because these are different, all right, these are different here, that tells me that the limit as x approaches 2 of the function here of f of x, all right, does not exist. And therefore, that tells me if the limit doesn't exist, well, the derivative at that point doesn't exist either. So that also tells me that f prime of 2 does not exist. All right? It's not differentiable at a vertex. So therefore, all right, a function is not differentiable at a sharp turn or a vertex. Is not, okay, underline the word not, differentiable at a vertex. Okay, we're talking sharp turn here. Sharp turn. Any sharp turn like that. That's a big conclusion there, guys. You could differentiate an absolute value function anywhere else, but not at the vertex. That's what I'm saying. Why? Because if the limit as you approach 2 right here at the vertex does not exist, well, then the derivative does not exist at that point, okay, because they're related. Now, the second type of situation that you're going to see where you don't, where the function is not differentiable, is where the tangent line becomes vertical. And since the slope of vertical lines are undefined, In some cases, you don't have differentiability there when the tangent line is vertical. And let's take a look at a situation like that, using the same definition here. So on this one, we're going to consider, well, first of all, note that the cubic function here, f of x equal to the cube root of x here. You can cube root any number you want, so it's continuous everywhere, first of all. Okay, it's even continuous at x equals 0, because the cube root of 0 is 0. I mean, it's defined there. However, is it differentiable at 0? And the answer is no, but why? All right, so let's do this. Let's investigate. What's the derivative at 0, using the same definition? And again, it's f prime, actually, let me just state it in general. F prime of c, and this is the definition on the preceding page, is the limit as you approach c of f of x minus f of c all divided by x minus c. Okay, that's how you find the derivative at a specific point. So let's find the derivative at 0. See if it's differentiable at 0. Right here, f prime is 0. That's what we're going to investigate. So to do that, let's take the limit as you approach 0 of the function, which is x to the 1/3, all right, minus f of 0, that's your f of c here, where c is 0, divided by x minus 0. Okay, well, f of 0 is 0 because the cube root of 0 is 0. So f prime of 0 equals 0 there. So you have x to the 1/3 minus 0 all divided by x. And that's equal to, let me see, that'd be equal to x to the 1/3 minus 1. Because when you divide like variables, you subtract exponents. And that becomes x to the negative 2/3. Let's write that as fraction, 1 divided by x to the 2/3 power. Okay. All right, let me insert my limit notation because that was kind of bad that I omitted that there. We want to take the limit as x approaches 0 here of all of these. You can't leave out your limit notation because you're investigating what the limit is. So my bad. So what we want to do is, what's the limit of this function here as x approaches 0? And remember, if you're approaching 0, it becomes infinitely small. All right, so what you're getting here is 1 divided by an infinitely small number. Infinitely small number here. And that becomes infinitely big. Infinitely big. So we say that it is approaching infinity. Okay, which is not a real number here. Not a real number. So why is that happening? Well, if you take a look at the slope of the secant line, let's consider P here and Q here. And the slope of the secant line is roughly here. And there's your secant. If you take Q and you slide it along the function here and get closer and closer to P, you'll notice that your secant line gets steeper and steeper. For example, if we'll call this Q1, put Q2 here, slide Q closer to P here, notice our slope of the secant line is steeper. And if you get Q even closer, let's put it here, Q3, you notice it's getting even steeper, and it becomes more and more vertical. All right? Vertical lines don't have slope. They have infinite slope. And remember, for limits to exist, they must be real numbers. And since infinity is not a real number here, the limit does not exist, and because of that, the derivative does not exist at 0. So therefore, function, which is x to the 1/3, all right, is not differentiable, okay, at x equals 0. Even though it's continuous there, it's not differentiable there. Okay, keep that in mind. So this is a good classic case that when the tangent line becomes vertical, the limit's is not going to exist, and it's not going to be differentiable at that particular point. In this case, at 0, even though it's continuous there. Okay. And then the third type of function, or the third case where a function's not differentiable at a specific point. Oh, let's say here's the function here. There's your f of x right there. The obvious case is where you have a jump. So let's suppose you're considering differentiability at c. we know that at jumps, the left and right hand limits are different. And so at a discontinuity here, at a jump discontinuity, you're not going to have differentiability there either. So the function, if it's not continuous at a particular point, it's not going to be differentiable there. Okay, why? Because f prime of c is equal to the limit as x approaches c of the function. All right, and that does not exist because the left and right hand limits are different. All right, because, as you already know from prior lessons, okay, the left, okay, and right hand limits, okay, are different. Okay, it looks like here the left hand limit is approximately 1, 2, it's around 3, and the right hand limits, it's like 3, 4, 5, 6, it's around 6. So if this is 6 and this is 3 right here, the left hand limit's 3 and the right hand limit's 6. They're obviously different, therefore the limit doesn't exist at that particular point at c. And if the limit doesn't exist, the derivative can't exist at c. And remember, the limit is directly paired up with the idea of the derivative and vice versa. The derivative is linked to the limit. So if the limit does not exist, the derivative doesn't exist either at that particular point. So if you have a jump discontinuity at a point, you're not going to be differentiable there either. Okay. So there you go. You've got. Let's review the three cases of where function may not be differentiable even though it's continuous there. So the first classic case is right here. The absolute value function, it has a sharp term or at the vertex. So at vertices, a function is not differentiable there, wherever that point is, because the limits at that point are different, causing the limit not to exist, and therefore the derivative at that particular point not to exist. Second case was that we have vertical tangent lines. So if a function has a vertical tangent line at a particular point, it's not going to be differentiable there, even though it's continuous there. And the third case is where, well, you don't have continuity because of the jump discontinuity perhaps. And because of that, the limit never exists there because the left and right hand limits are different. And because the limit doesn't exist, the derivative doesn't exist at that particular point. Okay? So these are the three classic cases. You're going to have to know these cases on your next exam here in Chapter 2. And then previous in the first part here, you're obviously working on finding the limits of functions, like these right here, or excuse me, the derivatives of functions using what's called the limit definition, which I talked about up here. So make sure you do your homework in full, make sure it's complete, make sure you know how to use this limit definition right here that I illustrated in the first part of the lesson on a variety of different functions from polynomial to root to rational. All right, and make sure you check your homework also in the homework file on my website. And I'll see you tomorrow. All right, work hard, make yourself proud.